So walking out of here today, you want to be able to write an equation to show the formation of 1 mole from its elements in the standard states if I give you a compound. And given a reaction equation and the enthalpy change, and I'm going to give you a couple of those. And then I could also give you instead a standard enthalpy of formation. You'll be able to determine the overall enthalpy of a process. All right, so remember that we have this delta H, but we're going to put a little F after it now. Okay, so this delta H with a little sub F is the enthalpy of formation. Okay, and basically this is what is going to be the value that is associated with 1 mole of a compound being formed. Now, we say from its elements that are in its standard states. And so if we talk about a standard state of an element, we are talking about something that is something like hydrogen, oxygen, the carbon. Just think about one of the elements on the periodic table. And so elements in standard states, which we assume then are at 1 atmosphere and 25 degrees Celsius, okay, we're going to say, if I start with, let's say I'm trying to form water, and I start with hydrogen and then I start with oxygen, then how much energy, right, the change in enthalpy, remember enthalpy is another word that kind of means like the heat, right, the amount of energy that's being transferred, whether it's being given off or released, given off or absorbed. How much energy is that going to take? Is it going to give off energy? Is it going to absorb energy? What's going to happen? So, for instance, if I look at water in the liquid form, and I look at the enthalpy of formation of that water, it says that it's going to be 285.8 kilojoules per mole, negative 285.8. And so that means that it is going to be giving off or absorbing energy. What do you think? Okay. Right, because we see that negative number again, right? And this is still enthalpy, so that negative number is still saying, hey, this is exothermic. It's going to give off energy. When I form water, it's going to be giving off energy. And again, if you think about what this is basically just hydrogen burning, right? Hydrogen and oxygen. If you take some hydrogen and ignite it with a match, you're going to be forming water. And that is definitely giving off energy, right? If you guys have ever seen hydrogen blow up, okay, good, nice little fireball, right? And so it's basically saying, hey, the amount of energy that it takes to form water is going to be such that it is going to give off 285.8 kilojoules per mole of that material. And so what we can do is we're going to rewrite this equation. Now, this looks kind of funky here, but notice how I put a 1/2 in front of my O2. Okay, so it's now H2 plus a half O2 gives me H2O. Now, the reason that I did this is because anytime I have this value of energy of formation, in this case, negative 285.8 kilojoules per mole, then I have to make sure that this thing that I'm forming is just 1 mole. So I have to kind of change my equation to make sure that on my product side, the thing that I'm producing is just giving me 1 mole of the substance. And so that's why I took and I put a half in there, and I don't have a 2 in front of the H2.
What about like the law of polymer ratios? Like, how does that work?
Right. And so this is not the way that we would write a normal equation because it doesn't follow that rule, which we are not allowed to have, these fractions, right? And so this is only being done in order to help us understand what this number is based upon 1 mole. And so it's just a quick way for us to make sure that we understand it's just based upon 1 mole, but we wouldn't write this out in that final sense with fractions if we were doing a balanced chemical equation. Good question. All right. So if we think about what hydrogen and oxygen are, anytime you get an element like hydrogen or oxygen, those elements are going to have values of 0, okay? Any standard element is going to have an enthalpy of 0. So the thing that is being formed is going to have an actual value, but the things that it's formed from, remember, those values are going to be 0, okay? So standard enthalpies of the elements are going to have a delta HF of 0, okay? And again, remember that these values are all in kilojoules per mole, and this is why we want to make sure that we put this product is just having 1 mole, whatever that is.
Where does the 1/2 oxygen come from?
So if we were writing our regular equation, remember if we were doing like this equation normally, we would have 2H2 plus O2 gives us 2H2O. And so because this is a kilojoule per mole, and that's just 1 mole, then what we do is we basically reduce this one that here, we reduce that down to a 1. And that means that we had to reduce this down to a 1 because we have to do the same thing to the whole equation. And so we had to reduce this down to a 1/2 because we basically divided everything by 2, right? So we wanted to make sure this was just a 1. And so that meant that this had to become a 1/2 and that had to become a 1.
Are the units always kilojoule per mole or no?
Yeah, so this unit here is going to be a kilojoule per mole. And so since we're doing enthalpy of formation, it's always based upon what 1 mole is going to be. So we have to change our equations when we do that. Good. Other questions? Okay. Now, these values are found on page R66. It's Appendix B, Table B14. So if you are looking in your books, you're going to see on page R66 a big table that has a whole bunch of these values. And so, for instance, you should go and look for water, which you'll see they have hydrogen oxide is how it's listed on page R66. And you'll see for the liquid form of hydrogen oxide, they have 285.8, negative 285.8. Notice, however, that's kind of interesting that the gaseous form of water is negative 241.8, right? So it's going to be a little bit less. It doesn't give off quite as much energy when it forms gaseous water as it does the liquid water. Okay? So you can see those. We're going to be referring to that table a lot as we go through this. So why is this thing happening? Why is it giving us, why are these reactions taking place? Why is it giving off energy? Remember that we are going to try to get to things that are typically going to be more stable, right? And so if I go from hydrogen and oxygen and I form water, if it's giving off energy, that means it had some potential energy in its chemical bonds that was released. So that means the new compound, water, is now more stable than the original elements were, right? So if you have a large negative enthalpy of formation, that means that this new compound is going to be really stable compared to what its original elements were. Okay, so big negative numbers means that you're going to get a much more stable compound than you had compared to when you started. So if we look at the enthalpy of formation for carbon dioxide, we can see that it says it's negative 393.5 kilojoules per mole of the gas that's produced. So does that mean that it's more stable in its compound form or less stable?
More stable.
More stable, right? So CH4 is going to be more stable than the carbons and the hydrogens that it was made up from, okay? So if I were looking, or I said CH4, CO2. So if I were looking in the book and I were trying to look for carbon and oxygen, I wouldn't have to find carbon and oxygen in that table on R66 because they're elements, right? And the formation of elements, or the standard state of the elements, is going to be 0. And so if I looked in the book on page R66, I'd find that value, negative 393.5 kilojoules. I'd find that for CO2, okay? If it has a positive enthalpy of formation, that means it just became a little bit less stable, okay? That was not a favorable reaction to take place in terms of stability. Okay, so why does a reaction take place if it's not going to be more stable? Well, it could be that, it is been, had enough energy added to it that it could form temporary bonds. So think about it. If I take water, water is more stable than the hydrogen and the oxygen that it makes up, right? If I take that water and I electrocute it through the process of electrolysis, then I split that water back up into hydrogen and oxygen. Okay, so that would be a less favorable process than, or at least energy stable, right? It's going to be a less stable process than if I were to do that in the reverse reaction. So we do have reactions going in both directions. And the value of this tells you that, okay? If it's a positive value, that means that it's going to be now its new product is less stable than it started with. And if it's a negative value, that means the new product is more stable than it started at, okay? So a good example of this is hydrogen iodide. Has a positive 26.5 kilojoules per mole. And because it's less stable, it's going to naturally decompose at room temperature back into hydrogen gas and iodine gas, okay? And so I can make this hydrogen iodide, but it's not going to stay that way in a stable form. If I just heat that up a little bit, just to room temperature, it's going to automatically start decomposing because it's not very stable.
So it decomposes just based off of what the enthalpy thing is. So like how, because it's a positive?
Yeah, because it's a positive, it's probably going to be pretty unstable. It's probably going to decompose pretty quickly and easily.
And so if it's like negative 393 like the other one, does it just not decompose, or does it take a long time to
It would just take a lot more energy to make it decompose. Like you can take carbon dioxide and you can break it up into carbon and oxygen, but it's going to take a lot of energy. It's going to be pretty hard because it's really stable when it's carbon dioxide. Yep, good question. All right, so here we can see some iodine vapor. Maybe that's hydrogen iodine gas there inside that chamber. Oh, or it could be NO2 is also another one of those gases that's actually brown. So what we want to do again is we want to write our equations where 1 mole of a compound is formed. So if we're talking about nitrogen dioxide, and if I'm normally balanced wise going to have a 1N2 and a 2O2 gives me 2NO2. Well, now I've got to rewrite it so that there's just one of these, right? So I have to divide that whole thing in half. And so then I can go to the book and I can look on page R66. And when I see that value, 34 kilojoules per mole, now that value can apply to this equation, okay? If I were to look at ethanol, this is methanol, and I were looking at methanol, and I'd want to see what the formation is. Again, in a normal equation that is balanced, this might have a 2 in front of it, but I can't leave a 2 in front of it because my value, which is my enthalpy of formation, is only for 1 mole, so I have to divide everything by 2. And so, like I said, just like on the water one before, this original equation would have had probably a 2 in front of that, would have had a 4 in front of that, a 1 in front of that, and a 2 in front of that. But because I need to know what the enthalpy per mole is, then I divide everything by 2, since that was a 2 there, so that this can become a 1, and then that becomes a half, that becomes a 2, and that becomes a 1. Okay? So just keep in mind that you have to do that when you are going through these. All right, so what would it look like if I were writing an equation for the standard enthalpy of formation for methane gas? How would I write that equation? So you're going to need to write the original equation, see what your numbers are, and if it's not 1 mole on the product side, if that's a 2 or a 3 or 4, like we have to divide that and reduce that so that it's just a 1. So write out your formation equation to make methane. So it's carbon and hydrogen, right? Carbon and hydrogen come together to make methane. Zoom kids, are you guys doing all right? Can you hear everything okay?
How many online
Okay. We got 4 right now. 2 kids that are with B and C. Now, that equation is going to have to include a number, right? A value from page R66. So make sure you look on page R66 to find the number. that will be included with your standard enthalpy of formation for methane.
Yeah.
Okay, so we want to start with carbon plus hydrogen, right? So what's the elemental form of carbon? The elemental form of hydrogen. And then that's going to make the CH4. And so then we have to see if we have to change that equation after we've started with carbon plus hydrogen. So it's methane, right? If we look for methane, we're going to find it.
How am I supposed to know that that's
How are you doing that? Yeah, that one is just because we've talked about it over and over and over again. That one's just kind of, yeah, it's just a methane CH4.
It's exactly.
It's the product. So when we talk about the enthalpy of formation, since it's CH4, then you got to make sure that that one is a 1. And if that one's already a 1, then you're good. If it's not, then you have to do that reduction.
Oh.
Look right to. Also, there's hydrogen, like, well, it's carbon that's solid or a gas one?
Carbon is a solid, yeah. Yeah. And then when they do enthalpies of formation, they might turn it into a gas in order to make it happen. Like, for instance, if they were to do something with sodium chloride, they would actually take sodium, which normally is a metal, and then they would basically heat it and electrify it, basically get it to a gaseous state. And so then those two are both at gaseous states, and then they put them together and then form sodium chloride. And so while carbon is a solid, when they do these formations, they might actually turn it to a gas, depending upon whether it needed to make that happen.
Yeah. That makes more sense.
All right, let's see how you did. Should have had the carbon and the hydrogen. Okay, remember hydrogen is H2, right? This is one of the Brinkelhoff elements, so we have to make sure we have H2 here. And so it's C and H2, but because we got to get 4 H's on the right side, then we need to have 4 H's on the left side, which means we need to put a 2 in front of that. Now, at this point, you might be like, well, do I have to change this and make this a half or divide it by 2? No. All you're looking at is this CH4. If that CH4 is a 1, and that's what you're looking for, the enthalpy of formation of CH4, then you're good. And you can just say, all right, well, now my value is, and if you look in your book, it would be negative 74.9, I believe, on page R66. Yeah, negative 74.9 would be the value you'd have for the enthalpy of formation. So negative 74.9 kilojoules per mole would be your enthalpy of formation. Okay? Questions on that?
I don't understand. So wait, why is it the 2H2? Like the second 2. I put that as a 4, yeah.
So remember that Brinkelhoff, do you remember what Brinkelhoff was?
No idea.
Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. All of those are diatomic elements. And so anytime you have an elemental form of one of these, then it's going to be diatomic, meaning that H would be an H2, right? Chlorine would be a Cl2. Bromine would be a Br2. Like any of these are always going to be diatomic, meaning that they have 2 atoms. And so if you ever have hydrogen by itself, it has to be an H2, which means that if I need to get 4 of them to balance out with the 4 that's over there, then I'm going to have to put the coefficient of a 2 in front of it to balance it out.
Sprinkle. Got it.
Does that make sense?
I thought it was a dude, but I got it now.
It is the chemistry dude, diatomic chemistry dude. All right, so we also have a value called enthalpy of combustion. Okay, so enthalpy of formation was how much energy it's going to be, giving off or releasing if you are forming a compound. But what happens if I burn a compound? What happens if I break a compound up and I am burning it, right? Complete combustion of 1 mole of a substance. And you'll notice we have a delta H, the little sub C there. And before we were talking about the products, now we're talking about the reactants, right? Because we're burning something up. So in this case, maybe we're burning up methane. And if we're burning up methane, now the methane is going to be on the reactant side. CH4, catching on fire, what does it turn into? It's going to turn into CO2, and since it's combining with oxygen, it's CO2 and H2O. And so I can say, all right, well, how much energy is going to be given off when I combust something? Okay, so when we talked about calorimetry, how much energy is given off when something is being burned, then this is part of the combustion process, right? So if I have 1 mole of reactant instead of the product, right, where we were talking about that with formation, then how much energy is being given off, okay? Now this is a bomb calorimeter, and we talked again about calorimetry a little bit already. And you can actually take in what we normally do, each year for lab is we actually burn some substance. We've burned nuts in the past, like little almonds that have tons of oil in them, and that's pretty cool. But it actually can cause some, irritants in the air for some people that have allergies to nuts. It's not exactly a good thing to have flying through the air. And we burn Cheetos. Okay, we can burn Cheetos as well, and you can kind of basically take the fire from the Cheeto and heat up some water and see how much energy it gives off. Well, a bomb calorimeter is a much better way to show how much energy is being given off in a substance. Basically, you have a little chamber, and inside this chamber you have whatever food you have, right? So how many calories does this food have? Well, you put that little sample of food in there. These are ignition wires, meaning that they're going to electrocute the food and catch it on fire, okay? And surrounding this whole chamber is this big tub of water, and this is just spinning the water to make sure it's circulating, and this thermometer is just changing, figuring out what the change in temperature is. So I electrocute this stuff, catch it on fire until it's burnt to a crisp, and the only thing that's left is residual carbon, right? And then, of course, gases would have been given off as well. And so once I've done that, I can see how much energy that gave off. And now I can tell you how many calories that food has. So you're like, well, how do they know how many calories a Snicker bar has? Well, they'll throw a little piece of Snicker bar in there, and they'll electrocute it, catch it on fire, burn it to a crisp, and see how much energy it gave off. And that's the value that they give to the calories that Snicker bar has. And basically the same idea is hopefully happening inside your body, right? Like you are taking that Snicker bar in, and your body's breaking it up into its fundamental, most basic components, right? It's taking the sugars and breaking them up into carbon and oxygen so that we're breathing out carbon dioxide. That's where that carbon dioxide comes from that you breathe out. It comes from the sugars that you eat. And so that's kind of the same idea. Here you have carbon dioxide as one of your products as well. And so this is what we want to do with our combustion chambers, right? We want to figure out how much energy is being given off. And so what this is going to do, this is going to take us now into Hess's law, okay? Calculate a change in enthalpy using Hess's law and the standard enthalpies of formation. And so now if I look at enthalpies of formation and or combustion, I can now come up with an overall change in enthalpy for whatever that whole process is, okay? So this is going to take us into what Hess's law is all about. So if I'm going from a set of reactants to a set of products, the total enthalpy change is the same whether it happens in one step or a series of steps. So I'm going to show you a couple of equations here, and you're going to see how you can kind of add these equations up. It's kind of like doing a little algebra problem where you have multi-step, algebra where you have like A plus B, equals C, and then you have, 2A plus 3B equals 4, and you can take the A's and the B's and you can kind of subtract and add them up together. Well, that's what we're going to be doing here. We're going to be taking our equations and we're going to be subtracting and adding them. Now, just like algebra, you can take these equations and you can manipulate them. You can reverse the signs, you can double them, you can halve them. You can just manipulate the heck out of these equations, just like you would an algebra equation, to make sure that everything, goes out to 0. Well, that's what we're going to do here. The idea behind Hess's law is that whether or not you split them up into A and B and C, or you have one whole big equation, everything is going to all be the same. Because these elements are all based upon the amount of energy that's stored in their chemical bonds. And so if I want to look at how much energy is stored in the chemical bonds, I can break that up into various different ways as long as I am using the same concepts. Okay? So if the reaction is carried out in a series of steps, the enthalpy change for the reaction will be equal to the sum of the enthalpy changes for the individual steps. Okay? Again, kind of think algebra here. I'm going to show you an example of this here in just a second. This lets us determine the enthalpies of reactions for reactions that are difficult to measure directly. In other words, there are some reactions that are taking place, but there's a bunch of little side steps, and you don't even know what's happening in some of these side steps that are happening inside the reaction. But if you can take an overall amount, and then you can equate that to the small little individual steps, those are going to be equal to each other, okay, and vice versa. Again, this can work for formation equations and also for things like the combustion reactions, okay? And if we have something that we know, then we can calculate these. Now, just like in algebra, if I decide to reverse a reaction, I have to reverse the sign or change the sign of my delta H. So if I was originally forming it and it was becoming more stable and I had a negative delta H, if I want to reverse it so that I'm breaking it up, now it's going to have a positive delta H. Okay, so if you reverse the reaction, reverse the sign. Remember that that sign is telling us the direction of the heat flow at a constant pressure. If the coefficients are multiplied by an integer, then I must multiply my enthalpy change as well. So if I have to, in order to get this thing to balance out, I have to multiply the whole thing by 2. Then I've got to multiply my enthalpy change by 2 also. Okay. Remember that enthalpy is an extensive property. Do you remember what extensive property is again? It's dependent upon the amount of matter, right? And so basically, the more stuff that I'm burning, if I have a bigger Cheeto and I burn a bigger Cheeto, it's going to give me more heat energy than a small Cheeto. Okay? It's based upon the amount of material, amount of mass. Okay. The last thing here for helping us figure out values with Hess's law is you want to work backwards from the required reaction to determine how to manipulate the given reactions. Okay, so when you're solving these things, you kind of got to start from the end and work your way backwards. From the required reaction is where you want to start. How do I manipulate the individual smaller reactions? Well, let me look at my big overall reaction, and that will give me a feel for it. Okay, get those rules down. Here's an example. Let's say I have a reaction where I'm producing nitrogen dioxide. Okay, now, right now, this says 68 kilojoules to produce that nitrogen dioxide. And if I look in the book, I can see that there are some other reactions. And sometimes your book will have these, sometimes it won't. We will give you these side reactions to help you, okay? Your job is going to be to figure out how to add and subtract, flip and double them and all that kind of stuff to get this one. And you're working backwards. So we're going to get to this. You got to start with this, and you got to work your way backwards. We're going to give you these other reactions, okay? If you weren't in the class, we might give you a big table. You have to look in the big table and figure it out. But we'll give you these other reactions that you have to use to get to this reaction. So here is one reaction. I'm making nitrogen monoxide, not nitrogen dioxide, but nitrogen monoxide. And that's going to be 180 kilojoules. I've got another one, right? I'm making the nitrogen dioxide, but that's negative 112 kilojoules. Is there something different? Yeah, look, there is something different. Up here I had N2 plus 2O2 gives me the 2NO2. Here I've got 2NO plus O2 gives me 2NO2. So even though I've got the same product here, my reactants are not the same up here. Again, I've got to work from this reaction, got to look at these other ones. How can I mess with these other reactions to get to this one? Now, if you're looking at this, you know that this is the product you want. You know you're going to have a 2O2 somewhere. And you know that you're going to end up needing one N2. Okay? So to me, if I look at this, and I'm thinking of algebra, and I'm thinking of adding things up and subtracting things, I can see that adding an O2 and an O2 is going to give me a 2O2, right? If I add those together. And remember, I wanted a 2O2 up there, didn't I? Okay? Now, anything that's on opposite sides of the equation, they cancel out. So this is kind of nice for me because I can see that 2NO2 and 2NO2, or sorry, 2NO and 2NO are able to cancel out. So I'm in a good place there because I don't want NO up here at all. And look, those two cancel each other out. I want an N2, and so if I drop this down, I still have an N2 here. And that's what I wanted. And I wanted a 2NO2. Look, I have a 2NO2 here. So this is kind of nice. Can you see how if I'm adding these two equations up, that it gives me what it is that I'm looking for? Just like if I were doing one of these in an algebra problem, right? AJ?
So you're going to give us the A and the B?
I would give you A and B, correct. And you just have to figure out, do they add up? Okay? Now, if they don't add up, now that's where you get to start manipulating things. You get to double things, flip things. And in this case, I didn't have to do it. It was nice and easy. It was, I could see that these things are adding up. And now I'm going to have to figure out what my kilojoules are, right? So if I add 180 and a negative 112, then I'm going to get a value. And guess what it's going to be, right? It's going to be 68 kilojoules. Okay, so what we want you to see here is that these equations are adding up to give you what you want. And this is what Hess's law is doing. Now, you are going to have to get a little bit more creative with the ones that we're going to give you. This one's a real easy one. Let's look at one that's going to be a little bit more complex. So here we want to figure out the enthalpy of formation for methane. What are the component reactions? In this case, they're the combustion reaction of carbon, hydrogen, and methane. Combustion reactions are three different things. Okay, carbon burning in the presence of oxygen gives me CO2. That's a negative 393.5 kilojoules. Hydrogen burning, and again, we want these to be, with 1 mole, right? Hydrogen burning in the presence of oxygen is going to give me water. That's a negative 285.8 kilojoules. And methane burning in the presence of oxygen is going to give me CO2 and H2O, and that's a negative 890.8 kilojoules. Now, if you're looking at these, Hess's law says we've got to figure out formation of methane. Now, we know the formation of methane. We just did this one, didn't we? We just did that. That's what we've got to get to. And what we want you to be able to do is we want you to be able to add up these equations to see if you can get to that. Now, is there a way that we're going to have to manipulate things? Do we have to reverse any of these reactions? Well, look at this. We want methane on what side? The product side or the reactant side? Product side. Do we have it on the product side here? No. So that tells us that we're going to have to do one thing in particular, and that's going to be to flip this, isn't it? We're going to have to flip that bottom reaction. If we flip the bottom reaction, what's going to happen? To the sign. That's going to become a positive sign, right? Okay, so that's one thing we know we have to do. And this is kind of what you have to do when you're doing Hess's law problems. You just got to look at it and see, how can I get to this equation that I want up here? And so I can say, well, I'm going to need, if this CO2 has been flipped, and that's going to have a chance to cancel out with that one, I want a carbon. I'm going to have to somehow make sure I get rid of my oxygens because I don't have an oxygen up here, right? And then I'm going to have to look at my waters and see if my waters are canceling out and see if that's right. So let me take you through that a little bit by bit. Okay. All right, so we talked about that first, and we're going to have to flip it. And so you can see that flipped, and that we changed the sign. And then you saw that we had 2 moles of water in the reactant. 2 moles will be needed in the product. And so we're going to have to multiply everything by 2 in order to make that happen. So we have 2 moles of water that needs to happen here. Because if you look back here, back to that previous slide, you saw that we had 2 moles of water here, didn't we? And this got flipped over to the other side, and so I'm going to need to somehow make this a 2 mole of water. If I'm going to make that a 2 mole of water, then I'm going to have to double this, I'm going to have to double this, I'm going to have to double that, right? And so that's kind of what we're trying to show you here on this next step, is how we're doing all that. Okay, so we doubled it, and that doubled our value over here, okay, so that we can see if we can now add them all together and see if they all cancel out, okay? All right, so let's see how they all cancel out now. So the O2 and the O2, that's 2O2. Those 2 are going to cancel out with that 2O2 there, don't they? The 2H2O cancels out with the 2H2O. The CO2 cancels out with the CO2. And now we can see what we have left. We have the C plus the 2H2 gives us a CH4. And so now we can add all of these things together. So negative 393.5, and add that to a negative 2 times 285.8. And then add that to an 890.8, and then we'll get our overall value, which is negative 74.3 kilojoules. Okay, now it's really close to what we had before, and then from that table, right? That table was negative 74.9, and here we probably got some experimental errors trying to show that. Questions on that? That make sense?
Great. On that bottom one, you know, like you switch the CH4 and to H2O. So you don't switch the signs on them, right?
You don't switch the signs on this part,
But you switch it in like this.
but you do switch it here. Yeah, good question. Because remember that these are actual like things that are being put together. So when that little plus sign means I'm putting this next to this. I'm putting them together. And so I'm not going to be subtracting them if I flip the whole reaction. It's not like I'm taking them away, and they're still putting them together. And so that's why that plus sign still stays a plus.
So besides just changing them where they were,
Yeah.
that's the only change that happens.
Yep. Yep. Good question. Others?
So why did you double the half the water first?
Yeah. So let's go back to that one. And let's look at that again. So we had in this original equation here, we had that there were 2 waters that would make this whole reaction take place. That's how you balance it, is with 2 waters. And so on this one, we didn't originally have a 2 in front of it. But in order to make it possible for these 2 to cancel each other out, we had to double the whole thing that was there before so that it could get a 2 in front of that. And then that way they could actually cancel out with each other. Does that make sense? And then that's why we put a 2 right there to say, hey, we doubled this whole reaction. And so instead of just negative 285.8, we have twice as much as that we have dealt with. Good question.
You do it based off of like what's at the bottom, and then you go to the middle and then the top.
Yeah, remember, you start with the thing you're looking for. So you've got to start with that one. This one right here, when we said, okay, the formation of methane. Well, that's what you needed to write out first. And you had to write this one out, and then you had to work your way backward. How can I get to this with these 3 things that I've been given? And remember, we'll give you all 3 of these you might have to come up with this one, formation of methane. That's not too bad. Carbon and hydrogen gives me methane, right? So you have to come up with this one a lot of times, but we'll give you these three, and then you just have to figure out how to manipulate those to give you this. Okay. All right, your turn. Woo-hoo, got 10 minutes. Let's see if we can figure out how to do this one. So you've got 4 PCl5, that's phosphorus pentachloride, is going to decompose and give you phosphorus and 10 chlorines. Brinklehop, remember Brinklehop? Chlorine, 2. Now, your equations that you get to use to try to figure out, how do I get this? Okay, you're trying to get to this from the stuff that we're giving you. So we give you this one, and we give you this one. Okay, can you figure out how to get, oh, it'll be all 3. Oh, yep, oh. That one's already done. Okay, so we give you those 2. Can you figure out how to get to this one up here by using these 2 here? So hopefully as you were going through this, one of the first things you noticed was that if I need to have PCl5 on the left side of the equation, then I'm going to have to flip that reaction, right? So hopefully you saw that this whole thing needed to be flipped down here, okay? So that it would have been PCl5 is going to give you the PCl3 plus the Cl2, okay? Now, if I flip that whole reaction, that changes that sign, doesn't it? So that should now become a positive. Then you should have noticed that if I wanted to get to 4 PCl5, I'm probably going to have to multiply the whole equation by 4. Now I'm going to have to multiply that whole thing by 4 as well, aren't I? Okay. And so now that I've done that, now I can say, hey, will everything cancel out? Let's just see. Now my 4 PCl3 cancels out with my 4 PCl3. I've got 4 PCl5 on that side, which is what I want. I'm supposed to have a P4. Oh, cool, I have a P4. I'm supposed to have a 10 Cl2. I've got a 4 Cl2 plus a 6 Cl2. Oh, that's cool, that's 10 Cl2. So now I've got it done. Does that make sense? You see that? Okay, so now I'm going to have to do that equation now with these 4, right? I'm going to have to do those 4 times that, and I'm going to have to add it to that. So let's see what our number is. Oops, go back. All right, so did you get a 1528? Raise your hand if you got that. Okay, here you guys. Awesome. Now, if you didn't get it, where'd you go wrong? Somebody volunteer a little help there. Where did you go wrong?
The first step.
Okay, what did you forget?
The flippage.
The flippage. No. So did you subtract instead of add?
No, I just didn't even flip the PCl5 over. I thought you were supposed to, I thought I was going to bring the Cl2 over, but then if you added, I was more focused on that first, like the A part that you gave it. Mm-hmm. And the 12th.
So again, always start from what your final answer is, right, and work your way backwards. And so take a look, when you do this, take a look to see if things are on the right side of the equation. And if they're not, that's a red flag, I've got to flip it. Look for that to see if they're on the right side of the equation. Cool. Any questions? Okay.